Hello and welcome to Selection with Sathi. Today we compare Python's three concurrency models from Fluent Python Chapter 20. Threading, multiprocessing, and asyncio each solves different problems. We will explore when to use each one, how the GIL affects them, and see the same spinner example implemented in all three approaches. First, let's clarify concurrency versus parallelism. They are not the same thing. Concurrency is about structure, managing multiple tasks that can make progress over time. Parallelism is about execution, tasks literally running at the same instant on multiple CPU cores. A single core machine can be concurrent by interleaving tasks, but not parallel. As Rob Pike famously said, concurrency is not parallelism, concurrency is what enables parallelism. The Global Interpreter Lock, or GIL, is central to understanding Python concurrency. It is a mutex in CPython that allows only one thread to execute Python bytecode at a time. This protects reference counting and internal data structures from corruption. But it means threads cannot run CPU-bound Python code in parallel. The good news, the GIL is released during I/O operations like network calls, file reads, and sleep. So threads can overlap on I/O waits. For CPU parallelism, you need multiprocessing. Python threads are real OS threads managed by the operating system scheduler. Create a thread with threading.Thread, passing target and args. Call start to begin and join to wait for completion. Threads share memory, making data sharing fast but requiring locks for safety. Because of the GIL, threads only speed up I/O-bound code, not CPU-bound code. Use threading.Event, lock, and semaphore for safe coordination. Multiprocessing creates separate operating system processes. Each process has its own Python interpreter and its own GIL. This gives true parallelism for CPU-bound tasks on multi-core machines. The API mirrors threading, process, start, join. The trade-off is higher overhead, process creation takes time, memory is duplicated, and data must be serialized to pass between processes. Use queue, pipe, or shared memory for inter-process communication. Asyncio is Python's single-threaded concurrency model based on an event loop. You define coroutines with async definite and pause them with a wait. The event loop runs on one thread and switches between coroutines at await points. There's no GIL contention because there's only one thread. Coroutines are extremely lightweight, about 1 kilobyte each. You can run thousands or even hundreds of thousands concurrently. Asyncio is ideal for high concurrency I/O, web servers, API clients, WebSocket handlers.
The spinner example from Fluent Python compares all three approaches. With threading, one thread animates a spinner while another runs a slow computation. The spin function loops, printing characters and sleeping for 100 milliseconds. A threading.Event signals when to stop. The main thread calls the slow computation and then sets the event. The spinner stops and we print the answer. Two OS threads running concurrently, simple and effective. The multiprocessing version uses process instead of thread. We import process and event from multiprocessing. The spinner runs in a separate process with its own GIL and memory space. The API is nearly identical, start, join, and event work the same way. The main process computes the result and sets the done event. For this I/O-bound spinner, there's no advantage over threading. Multiprocessing shines for CPU-bound work where the GIL is the bottleneck. The asyncio version uses a single thread with cooperative switching. Async definite spin loops forever, printing characters and awaiting asyncio.sleep. Async definite slow awaits asyncio.sleep for 3 seconds and returns 42. In async definite main, we create a task for spin, then await slow. When slow finishes, we cancel the spinner task. Everything runs on one thread. Await points are where the event loop switches tasks. No locks needed because there is no preemptive switching. The sleep experiment reveals the scaling limits of each approach. Launch 100 sleeping tasks in each model. Threading takes about 1.1 seconds and uses 8 megabytes. Each thread is about 80 kilobytes. Multiprocessing takes about 1.5 seconds and uses 200 megabytes. Each process is about 2 megabytes. Asyncio takes about 1 second and uses just 1 megabyte. Each coroutine is about 1 kilobyte. Asyncio can scale to 100,000 concurrent tasks. Threads hit limits around 5,000. Processes around 1,000.
Essential tips for choosing the right concurrency model. For CPU-bound work, use multiprocessing to bypass the GIL and leverage all CPU cores. For high concurrency I/O with thousands of connections, use asyncio for minimal overhead. For simple I/O concurrency with tens of tasks, threading is easiest and works well. And remember, you can combine all three in one program, asyncio for I/O and process pool executor for CPU-heavy work. For more concept videos like this, download the Selection with Sathi app. Like and subscribe. Thank you.